Hmm?
So, question is that it gets arbitrarily close to L. Like, what if it goes L at some point before infinity?
Even better because
It's also called a limit or just
also limit. I mean, that's mean it achieved the limit. Is everyone back? Seems like you guys don't need that much break, is it? Still can cope. Okay. Look like not all of you came to that, is it? Or you guys just have this many students? Us here have 48. I don't think there's 48% here. So I pass down this attendance list. Please do not sign for your friend. Your friend should email me, talk to me why they come back here. Then I will. Okay, it's about 1 more minute. I forgot to press record button just now. So I just start from another hour. Okay. One of you asked me, what about it? What about if the sequence is just L for everything at the back? Okay, so meaning it become a constant sequence eventually. Okay, so the limit is still the same. So this problem is exactly the continuity problem. Okay, so you have a limit to that point, but you can either achieve it or you don't achieve it, right? I'm not sure how you are taught in calculus 1. Do you guys start with sequences first or not? No? Okay. So supposedly, at least for me, when I study, we start with sequence converging and then we start talking about limits and then continuity. And then, yeah. So for example, I let you see an example here. So what is arbitrary close and versus equal to? For example, this graph here, EX. Right. So let me see. So this curve get arbitrarily close to y equals 0, but never touches it. But no matter how close you want it to be 0, you can find a far enough term that is as close as you want to 0. Okay, that's what we meant by arbitrarily close. Okay, but it doesn't equal to, because you cannot find a point that evaluated to 0. Okay, can differentiate these two concepts now. Okay, but so equal to is a subset. So infinite equal to L or arbitrarily close to L. Okay, it's a subset. So it's better if you have infinitely term. So it become a constant sequence after a certain term. After finitely many terms, it becomes constant. Okay. All right. So yeah, so in this case, we want to find limit of certain sequences. Okay, so how to find it? So one way is to find from the limit of function, which we have learned before. So let's put as a theorem, first theorem in the class. We won't prove this. So if the limit of fx equals to L, then limit of n to infinity of fn is equal to L2. Okay? So does anyone not know how to read this kind of passages or sentences? Okay, just remind you again in case you don't know, because later the proposition will get as complicated as it wants. Okay, so when it is complicated, you have more condition to check, and then more condition you need to consider, and then what sort of result that it will give by this theorem here. Okay, so now here is very simple. If P then Q, okay, give me P, I'll give you Q. Okay, if P then Q. So if you want to have Q, then you need to find P. Okay, so for this kind of theorem, normally we were interested at this Q part here. Okay, so we want to find when the function evaluate at so there's some rigorosity here. So I should say x is in R here, and then n is in natural number here. Okay, so they put x, usually they mean for all the real numbers, n for the natural numbers. Okay, so when a function evaluate at the natural number, what do you get? What do you get? Also natural number? Not exactly, but you get a sequence, right? Remember this picture here. So I input 1, you give me one number. Input 2, you give me another number. Input 3, you give me a number. Okay, so you can think of it as a function on. Okay, so let me draw more stuff here. So as a function from natural number to real. Okay, so you can think of it a sequence as a function from natural number to real. Okay. Okay, so this sort of complexity, I think it should be expected. Okay. Yeah. So, but if you consider all the real number, the formula should make sense as well. Okay, because you just plug in the number in. Okay, so let's give an example. So always when we talk about abstract concept, right, it's better to have an example. Okay, for example, let's find the limit of n to infinity of 1 over square root n. Okay, so here, what is our an? What is our an? An equal to what? Huh? An equal to what? A 1 over square root n. Okay, so a equal to 1 over square root n. So it doesn't say where it starts, so we'll assume it starts from 1. Okay, so it's assumed it starts from 1. So the idea of limit is you see what happened at far end. Okay, so for example, a equal to 1, we have 1, and then 1 over square root 2, 1 over square root 3, 1 over square root 4, 1 over square root 5, 1 over square root 6, 1 over square root 7, 1 over square root 8, and so on. Okay, so can you guess what's the limit is? Just guess. 0. Okay, let's see if it is a 0. So what we have done previously, so we try to plot this sequence here, right? And then see what it approaches to. So you start from 1, okay, 1 over square root 2, maybe here 1 over square root 3, and so on. Okay. Okay, seemingly is approaching to 0. Okay, but how to prove it in rigorous? So in mathematics, when you say something is true, right, you must prove it. Okay, you don't just say it looks like close to 0, so it's 0. No. Okay, so you need to prove it rigorously from the definition, or you have some gadget. In this case, we have a gadget. So if we can show that this, if we define on the real line and we find the limit is 0, then we will know that this will approach to 0. Okay, does it make sense? Okay, so the strategy is like this. So let's look at the, okay, I cannot call it sequence anymore. The function 1 over square root x defined on x. Okay, so and compute the following. Okay, so in the theorem, it suggests that we need to look at x to infinity of 1 over square root x. Okay, so what's this? What's this? How is it limit introduced in calculus 1? You just take L'Hopital, okay, one of it, huh? Left and right limit. Oh, left and right limit. Oh, okay. But this one is going to infinity, so you cannot do left and right. Just do left. Ah, okay. So what's the left limit of this thing? Huh? 0. 0. Okay. So even for limit, there's also another rigorous, limit for um real value function. There's also a rigorous way to do it. We call it a delta, epsilon delta definition. But we don't do it here. So we assume you know how to compute from calculus 1. If from calculus 1 you compute this one is 0, then it should be 0. Okay. Okay, so from calculus 1, we know that this limit is 0. Then by theorem, if we change the domain to, if we change the domain to natural number, the limit is also 0. Okay, so in this way, we should show that it's a limit to 0. Okay, is it clear? So this example is to show you how to use the theorem. Okay, so you can resort to the method in calculus 1. Okay, use the limit on real value function. Okay, next. Okay, next, I want you to think about this and discuss with your friend. Does the sequence -1 to the n converges? Okay, I give you about 3 to 4 minutes. You can discuss with your friend. Try and write down this sequence and then see if it converges. If it converges to what number? Yeah, try and figure out whether this sequence converges or not. What, any answer? I heard some of you got answer. Any idea? You can try to write down these what's this sequence here? I like to draw a picture because I like geometry. So you can draw some picture to help you if you want. Okay. Anyone have any brave answer? Anyone have a guess? Huh? 0, converge to 0. Okay, so let's say if we say it converges to 0, is it true? Okay. So what's the definition? So whenever we talk about this thing, right, we should always go back to the definition. All right. Definition says what? Okay. Definition says that the values of an get arbitrarily close to L. Okay. The L we guess just now is 0. Arbitrarily close to 0 when n is large enough. Okay. Let's see if this number get arbitrarily close to 0 or not. Okay. So you can see that if I pick, for example, 8, okay, how far is it from 0? It is 1 away from 0. If you pick 9, how about pick 9? Okay, let us pick 9. Let's extend this axis a little bit. So if we pick 9, it is -1. -1 is still 1 away to 0, but you want it to be arbitrarily close. Okay, so meaning if I want to say about 0.5 close to it, 0.2 close to it, or 0.00000001 close to it. Okay, you can see that from this sequence, right? You can never find some point that is arbitrarily close to 0. Okay, you can never find this point. Does it make sense to you? You look confused. No, right? Okay, no. If no, right? Okay, this is a normal process in learning mathematics. So you need to come back from this definition here. Okay, when we say something has a limit or converge to L, we want to find n such that the term inside your sequence is arbitrarily close to L. So what does it mean by arbitrarily close to L? I want to find the terms as close as I like to the limit. Okay. So for the case just now, I need to find the term as close as I like to 0. Can you do that? For this sequence here, can you find the terms that is as close as you like to this limit, to this 0? Can or not? Cannot, right? Because they are just revolving around 1 or -1. Okay. Okay, so by definition, this doesn't converge. But whatever I say just now, right, can write rigorously using epsilon delta definition. Okay, so anyway, so since the sequence alternates between -1 and 1, therefore, okay, not therefore, since cannot put therefore, so it does not converge. Okay, so in this case, by definition, if it doesn't converge, it diverge. Okay, so this sequence diverge. It doesn't diverge to infinity, but it still diverge. Just that you cannot find a limit. If you learn lim sup and lim if, right? So actually you can see that there's 2 limit it approaches to. So this is extra stuff. You don't need to know, but I just give you an idea. So actually you can see 2 things it converge. You can found 2 limits up and down. Okay. In future you will learn something called lim if and lim sup. Okay. So one of them is lim if infimum, one of them is limit of supremum. Yeah. Okay. This is just extra stuff to give you an idea. But general limit, it doesn't converge. Okay. Okay. Next. So we have properties of convergent sequence. So if our limit is converging, sorry, if our sequences are converging, then we can look at some linear combination of them, okay, or some combination of them, not just linear. So let's take two convergent sequence. In your mind, you should have some convergent sequence in your mind. What's the most obvious convergent sequence? Can you think of an obvious convergent sequence? Sorry? 1 over s squared. Yeah, okay, but there's even more obvious one. Yes, constant sequence. Okay, so it converges to itself. Okay, constant sequence, or the zero sequence. Zero sequence also converge to itself. Okay, so this is the first one actually. This is the first property here. So if you take a constant sequence C, it will converge to just C. Okay, and then if you take a convergent sequence AN, okay, and you multiply everything with C, okay, so you scale your sequence with C. You want to guess what you get? It's just C times the original limit. Okay, so you can see that this lim is a bit like linear operators. Okay, linear operators. Because sequence form a vector space, right? If you have learned in linear algebra. Okay, anyway. So trying to link whatever you learn together. Okay, so let's say if I add or minus two sequence together and I want to find the limit. Okay. So what's the result? You can guess. Yeah, you can actually show that it is just taking two limits and plus or minus them together. Okay, so this is really like linear function. Linear operators. Therefore, not only that, let's say we multiply two convergent sequence together. Okay, we also can just multiply the two limits together. And fifth, what do you have? We can also divide the two sequence together. So how you divide two sequence? You divide term by terms. How you multiply sequence together? You multiply term by term. This is suggested in this notation here. N times n. If I write n times n plus 1, an times bn plus 1, that means I need to pick the first one and then the second, the n plus 1 term from the second term. Okay, but in this case, we just match the two sequence together. So in this case, it's also lim of an over lim of bn. Okay, so note that every time we divide by a number, you don't want the denominator to be 0. Okay, so there's an extra condition. So what do you think about this property? Is it convenience or not? Whenever you see this kind of property, right, you should think that this is a convenient, because I tell you that if you do this operation, right, you don't need go back and try and guess or try and find from first step what's the limit, but you can use what you already found for the original sequence. Okay, so these kind of properties seem trivial, but it gives you an easy way to find a limit for new sequences based on what you have before. Okay, all right. Do we have examples? Okay, we have examples. Let me show these examples. Okay, example. So find the limit of 3n squared over 7n squared plus 1. Okay, so let's say we want to find this limit here. Okay, So what's the first term? So the first term is 3/8. Second term, 16 minus. Okay, I don't want to compute. Maybe put this first. And then 9, 27. Wait, what am I doing? So 1, so 2, 2, 2, 4, 2, 4. So 3, 3, 9, 3, 9. And then so on. Okay. So I think seems a bit complicated. Okay. So what to do? So what to do? So what to do? Actually, this example doesn't contribute to my theorem. This example is just like example for the previous theorem. Okay, this example actually worked for previous theorem. Let me see if there's another example. Okay, maybe we'll do this example first, and then we do another example that actually uses the property of limit sequence. Okay, actually, there's one way to see this. So let me write it out. So in limit, right, you always have a trick. You can multiply 1 to that function. Okay, so what you can multiply? You can actually multiply 1/n squared. Okay, because if you want to use these previous properties here, right? Okay, I think the closest one is this guy here, right? You have 1an/bn, so which is 3n squared over 7n squared plus 1. But you need to start with a convergence sequence, right? So if you put 3n squared, what does it converge to? It's diverge, right? Also 7n squared plus 1 also diverge. Okay. So you really can't do much here. Okay. But if we modified it, then maybe it can. So let's modify it. So I multiply 1 to both to the function, but I end up with a simpler case. I get 3/7 plus 1/n squared. Okay. So in this case, the numerator here become a constant sequence. And then the denominator here become 7 plus a converging sequence. Okay, okay. So let's show it. So have we shown? Okay, never mind. So maybe we need to first show that this is 0. Okay, how do we show that this is 0? Anyone remember how we show that limit n to infinity 1/n squared 0? How should we show this? Based on what we can use and have learned. 0, yeah. Why is it 0? Uh, hmm. Okay. Actually, that definition, right, is not very useful because I didn't precisely tell you what does it mean by arbitrarily close. So it is not quite useful, that definition. But I provide a tool for you. Remember the first tool we learned? Who can remember what's the first tool we learned? And let me remind you. This tool. Okay. So if you want to show some sequence converge to some limit, you just need to compute the limit for the real value function. Okay. So if the real value function converge to 0, so I can write if lim of x go to infinity of x squared is 0, then this thing will be also 0. Okay. Yeah. So that's why we immediately repair the, how's that, the inefficiency of our definition, because that definition can't be used to show anything useful, but maybe it will help you to see why something is not true. Okay, but it's not useful to show something is true. Okay, to show something is true, you need to go to a more rigorous definition. Okay, so we can see that this one is converging, this one is converging, right? Because the constant 7. So when two convergent sequence add together, the limit also add up. Okay, when the numerator is converging, the denominator is converging, then the limit of this quotient sequence is just the limit of the numerator over the limit of the denominator. Okay, so this is the whole thing we want to put in here. So okay, so let me write it down. So since 3, 7, and 1 over n squared are converging, converging by properties of what? Of the, how do I call it? Property of limits of sequence. Limits of sequence. Limit of n 3 plus 7 over n squared is equal to limit n to infinity 3 over limit n to infinity 7 plus limit n to infinity 1 over n squared, which is 3 over 7 plus 0, which is 3 over 7. Okay. So in the tutorial, in the assignment, right, I want you to write until this form. Okay. Whenever you use theorem, use properties, I want you to make sure that you are following the condition first before you use it. Okay. So for if P then Q, if you show me Q, you need to show me why P is true first. Okay. Is it clear? You need to write until this kind of rigorosity. Okay. By what? So every step, every equal sign by what? By what? By what? By what? Okay. You cannot just claim that it is equal, is equal, is equal, is equal, is equal. Okay. So everything have a reason one. Is it clear? Clear? Okay. Yeah. So if I skip some step, you should also like ask me, and I should fill it in. Okay. Okay. Let's see. Okay. Let's see. Maybe we do one more. Maybe we do one more. Maybe we do one more. So examples. Does the sequence n over square root en plus 2 converges? Okay. If yes, to what number? If yes, to what number? Okay. So you can see that both bottom and top doesn't seem to be convergent sequence, right? Is it 1, 2, 3 until infinity, and then the bottom is square root something that's increasing as well? So what to do? Any idea? Huh? What? Divide. divide by n. 1 over n. Okay, divide by 1 over n. Let's see what we get. So let's try divide by 1 over n. What do we get? So I divide by 1 over n. What do we get? We get 1 over, what is this? N square, right? So e over n plus 2 over n squared. Then in this case, the bottom here will converge to something 0. Is it? Yeah. Right. So we cannot, okay, although both of them are converging, but just now remember we don't want the bottom one to converge to 0. Right. So maybe this is not quite helpful if we want to use the what? The formula. What to do? Maybe we can divide by something smaller, square root n. Okay. So what we get at the top is square root n, and then the bottom we get e and square root n. Okay. Hmm. So what about now? What about now? What about now? Okay, so we are actually multiplying 1 to this sequence, right? Okay, so it's like we are doing nothing to this sequence here. But from here, there's something quite obvious here. You can see it or not? So if you look at this sequence, right? Okay, if you look at this sequence here, I write something stupid. This one is n should be the same. So if you look at the sequence here, the denominator here, when n get large, this term will disappear. Okay, so you left with square root e. Correct? Okay. But the term here will keep growing. So actually this is diverging. Okay. So I think this question doesn't use any properties because there's no convergence sequence here. Okay. This is just some trick using multiply by 1 to change your form to a better recognizing form. Okay. Okay. So this trick is very important in this course, I guess. This course always do this kind of a thing. So you multiply by 1, but that 1 is very special so that you can cancel some variable out and then to help you find the answer. Okay. For calculus, I think this one quite very important. Algebra also need, but anyway. Okay. Okay. So how about next? Uh, what time is it? 3:38. 3:38. Okay, how about let you do this question here? So I give you 5 minutes. Figure out whether this sequence converge or not. Try and find whether this sequence converge or not. You can discuss with your friend if you need. As I always told my student, don't be discouraged if you cannot finish. Okay, it doesn't mean for you to finish. Okay, it is about how you start and then how you work. Okay, I mean during my uni times, we never finish tutorial question during our tutorial time. Yeah, so it's about how you start, how you get stuck, how you unstuck. Okay, this is real life. You can't finish everything on time. Okay. All right. So any idea? Anyone have computed it? What do you get? 0. Okay. How do you get it? L'Hopital's rule. Okay. Cool. Okay. Good. So you can use L'Hopital rule. Okay. So why you use L'Hopital rule? There's no function here, right? Okay. What? First one. Okay, so you make a real value function out of this sequence, okay? Because we have the first two where if we found the real value limit for this function, then the sequence will also have the same limit, right? So if you can find this L, then this L will be equal to the limit of the sequence. Right? Is it what you mean? Okay, good. So as what's your name? Wensu? Wensu, okay. So as Wensu suggests, so we want to use L'Hopital rule. So what's the condition to use L'Hopital rule? Anyone remember? Oops, not here. Uh, anyone remember what's rule for using L'Hopital rule? Say again. Huh? Say again. Indeterminate form. Indeterminate form. What do you mean? Okay. So not sure. This one a bit different from my version. Okay, if I'm not wrong, so a so I should write it here. It's infinity fx gx is equal to the limit of x fx gx prime and f prime. Okay, so these two are equal if what condition holds? If both of them are infinity. Huh? What? Ah, okay, wait. Let me write down first. If fx gx equals to infinity, and then what else? Both equal 0. Is it? Okay. If fx is 0, gx is infinity, then you get 0. Right? 0 over infinity. Does it include infinity over 0 or not? No. No. Okay. No. Okay. So this is the L'Hopital rule. By the way, I will check if it is wrong or not. But I think it's pretty correct. Just recall. Okay. So in this case, we see that ln x go to infinity when x get to infinity, x get to infinity when x get to infinity. So on the left-hand side, we have by L'Hopital rule, we get what? The differential of ln x, you get 1 over x. You differentiate x, you get 1. So it's just limit x to infinity, 1 over x, which is 0. Okay, so L equals 0. So that means your sequence also converge to 0. So the sequence ln over n converges to 0. Okay. So another way you can think of this this converging is actually the top what? The top function decrease faster than the bottom function increasing. Okay, that's why you can converge to 0. Make sense? Okay. So I think ln x. Okay, let me graph. So ln x. Is it true that ln x look like this? Or am I wrong? Okay, sorry. Hey, ln x, this like this, right? Ln x. And then x. Is it true? Okay, I'm right there. Okay, so it represents some ratio between them. Okay. The rate of change, right? We will learn it at the back of the chapters. Okay, behind the chapter behind. Okay, before we take another break, let's do another theorem. So we have a 2 using real value theorem. We have another properties of convergent sequence. Now we will learn the third one. So we will learn the squeeze theorem. So what is squeeze? I think you know what squeeze is, but what is get squeezed? So suppose that AN and CN both converge to L. Okay. And you got a sequence that squeeze between these two sequence. Okay. You get another sequence that squeeze between these two sequences. For every n greater than n. So this means maybe it doesn't get squeezed for finite n, but it gets squeezed after a finite term. After a finite term, it gets squeezed. That's fine. Okay. So we don't. So for sequence, right? If you look at the converging, the definition of limit, we only care n that is far behind. We don't care finitely many n. Finitely many n is very far from that limit. That's fine. As long as for further enough, I can find terms that's close to the limit. Okay. So for all n, then so suggest by this theorem, this limit of Bn is also L. Okay, it's actually equal to the limit that An and Bn have. So pictorially, you should have this. Okay, so put a 0 here, put an n here, put an an. Okay, here's so many an, so many put r here. So maybe we got a coming down. Okay, for example, and maybe we got a c maybe going up like this. Okay, they converge to some l. Okay, so let it converge then. Let it touch, or maybe don't touch. Okay, but you got a b that running across. Okay, so I made it more exaggerating. So after a certain n, so maybe I call this an n, then it becomes something in the middle. Okay, this one a bit irregular, sorry, but never mind. You will see this kind of stuff maybe in real life and then. Okay, so this is a proof by picture. Okay, actually you can write a formal proof for this, but this one is a proof by picture. So after an n, everything stay inside this region here, and it won't go outside the region. This is the most important part to show that the limit of Bn is actually L as well, because it doesn't go outside the range. Okay. Okay. Yeah. What time is it? 3:50. Okay. So yeah, so you can see that the way I teach maths, right? I don't just do exercises or teach you method. So every time when we do an exercise, I want to like dig inside what's the concept behind. Okay. So because if you just do exercise, I mean question will change. Okay. If the question change, then most probably you will lose. Okay. But the underlying principle is the same. So if you know the principle, whatever question I throw to you, you should know how to do. Okay. So most importantly is the concept. And I also put up, so if you want, I will assign some of the questions from Stewart, but I can tell you that don't be contented with doing those exercises because it's not enough for you to understand. I mean, if you are good, maybe you can understand, but if you are kind of people that need to do more, you should do more. Okay. When I assign the question, you should do those questions to help you to know what's going on. But to get better result, you should do similar type of question. Okay. And then I'll put up another version, another textbook with solution. Okay. So if you cannot work out some problem, you can look at that solution and then try to understand. And then forget about it. Look at the question again, redo from your perspective. Okay. We end at 5 o'clock right today. Okay, let's take another break and then we will show the example for squeeze theory. We will come back at 4:02. I'm just curious. Anyone drop this course or not? I mean, drop this degree or something like that? Or anyone is a friend of Li Ziwing? Li Ziwing. Li Ziwing. Anyone know? Don't know. Li Ziwing. Dan Jing Seng. Anyone friend of Dan Jing Seng? No. No one know. So you guys don't know each other, is it? Okay. That's fine. Your friend. Oh,
So back at the next semester.
or differ.
Okay.
Okay. Okay. So already inform AA or
Pretty sure if he,
I think AA haven't informed me.
Oh, I'm pretty sure he already did the
Okay, application.
yeah, but I'm not
Okay.
sure if he informed them.
Okay, okay.
trying to pronounce F kind. It's in
Oh, I mean, okay, I know.
so which book do you
Actually, it's this book. Later, I will say again, but actually, it's this book, but I'm not sure it's the same version or not because sometimes the patch doesn't match up.
Oh.
But you can find the right chapter. The question is almost the same. But I will post later. I will post question from here. Yeah, because that one is a previous year. You receive. Yeah. I will make announcement as well. Okay, so in the first lecture, I tried to go as slowly as I could. Then later on, we will speed up a bit because some question maybe will be left as homework, and then maybe some tedious word we won't discuss will left as homework for you to verify. Okay, so that you at least you know what and whenever I talk something, you will know what I'm talking about, and then later you can verify yourself. Okay, so I know some of you concerned about this exercises here. Because this is when I posted it's a previous year notes, so maybe it's based on different version, but I couldn't find that version either. So one remedy is you can go to my textbook version and then look for the chapter and then look for this number here because they are mostly the same, the question pattern. Or after the lecture or before lecture, I'll post up the number that matches the version that I put on the PDF on Moodle. Okay, so I'll put question. But as I said just now, so don't be contented with doing this question. Try to do as more as you can. Okay, I provide a lot of reference for you to see. Okay. Is my note. So squeeze theorem. So examples. So let's look at examples. So let's find the limit of the following. Okay. So what's the sequence here actually really? What's this sequence here? I forget to prepare this from this picture here. So, okay, so let me draw something. So let's see if we can derive from principle. Maybe not can, maybe just some xy. Okay, so for sine cube n, right? What is sine n? Sine n repeat within 1 and minus 1. Right? And then for further sine, you divide by further n. Make sense? Okay. So I go between 0, 1, 0, minus 1, 0, 1, and then minus 1, and then come back to 0 again. Okay. So maybe it's something like this, something like this. Okay. Because when n is further, you divide by more n. Okay. But you always get back to 0. So I get something like this. Okay. Okay. So since we want to use squeeze theorem here, actually, I really need to show you the picture first so that you will know why we want to use squeeze theorem. But maybe I will show you next time. But how to use squeeze theorem? Do you have any idea what A and C can use to bound this function here? Zero? What? Say again? 0. This? 1 over x, 1 over n. Huh? What? Okay, negative 1 over n and 1 over n. Okay. So you suggest us to bound this way. Why? Sine n is in between 1 and minus 1. Okay, so if you take the cube of it, the numbers still lie between 1 and -1. Then you can divide n on all of them. Okay. So so to use squeeze theorems, okay, so to use squeeze theorem, so this is true for n, okay? So in particular, n greater than 1. So you can pick n equals to 1, okay? So since limit of n to infinity of 1 over n is equal to the limit of n to infinity of 1 over n. Should I explain again why this limit is 0? Okay, actually, really, when you want to put all these things out, right, you should say since the real function of that function. Okay, let me write down. So since the limit of x go to infinity of 1 over x is 0, and the limit of x go to infinity of 1 over n is 0. Okay. So if you really rigorous, you should start from here, okay, and then conclude this. After you conclude this, then since this is 0 and this is true, and this sequence is bound between -1 over n and n, squeeze between 1 over n and n, -1 over n and n, we have the limit of the middle sequence also converge to 0. Okay? Yeah. Okay. Straightforward. Okay. Okay. So next, about next. Any question, by the way? Any question? No question? Okay, continue. I think you guys quite good, eh? Last time the classes I taught, every time I say something, they get confused. Okay, never mind. Anyway, okay, quite good. Maybe we can increase the level of difficulty. Okay, so show that if this the absolute value of a sequence is 0, then n equal to infinity of an is 0 as well. Okay, so this kind of question is what you should expect in your assignment, but not every question is like this, but some question like this should be, because this is a pure math course, right? So this says that any sequence, right, if it satisfies the absolute value of that sequence, and you look at the limit is 0, then the original limit is also 0. Okay, so why is it true? Since this is listed under squeeze theorem, right, so you should think of a way to use the squeeze theorem. So why is this true? I don't tell you what's the sequence now. Any sequence that satisfy, if you take the absolute value of that sequence, so you throw away all the plus minus sign, and then you found out that the limit is actually 0, then the original sequence also converge to 0. Why? Huh? Why? What? You got any idea? Mumbling something. You want to say something? Okay. Sure. Okay. So how do you use this fact to show it? It's actually converged to 0. Let's calculate the limit of two sides. So let me write down first, then you can continue. So what's the limit of the right-hand side? How to compute the limit of the right-hand side? Left-hand side, sorry. How do you compute? Why is it 0? Huh? Why can you take out -1? Which term? It's a constant. Okay, it's a scalar. Okay, right. So you use the property of the limit of sequence. Okay, because an is converging, -1 is a scalar, so you can take out the scalar. Remember, I told you that the limit is kind of a linear operator. Okay, so you take out these, and then you compute this. So this one is so rigorously you should write by property of limit. Okay, I don't write everything up. LOS limit of sequence. So it's equal to -0, which is 0. So here is by assumption. Right, you assume that the limit of the absolute value is 0. Okay? So the right hand side easily fall out just by assumption. Okay. So make sure you write every step reason why it is true. Okay, don't just write equal. Okay. So write out everything. So it must be explicit. And okay, so we know that the left is 0 and then the right is 0, and then it's squeezed between these two convergent sequence. So by squeeze theorem, we know that the limit of an is 0. Wow, I combine my then and my my sequence, my left arm and limit. Okay, so by okay, so this is true for all n. Are you guys okay with this notation for all? Okay, so by squeeze theorem, limit n to infinity an is 0. Okay, done. Okay, so there's an example in the book in the previous year. Not, I'll left it as a homework. I'll provide the solution later. So it is this one. So alternating function of 1 over square root n. Okay, so this one left as homework. Okay, this one should be similar to what we did before. So skip this one. You can do at home, and then I'll provide the solution. Okay, the next part is important because we were going to use this over and over and over again. So I want you to try and figure out what's this. So the question read like this. So for what values of R is the sequence Rn converging? Okay, so actually I need to tell you where these R live. Okay, so this R live in the real number. So the whole real line you need to consider. Okay, so when is R to the power n converging? I give you 5 minutes. Okay, try and work it out. Try and discuss with your friend how to start. Try and discuss with your friend. Maybe you can start by finding an R. Try with one R, and then try with a few R, and see what you get. Try different R in the real life. Yeah. Yeah. So this kind of question, right, is very helpful that you start with some particular example. So you can pick R equal to 0, R equal to 1, -1. Those that are easy to calculate first. And then try and figure out if there's any pattern hiding inside. Try discuss with your friends. Yeah. When is R to the power n convergent? Try R equals, okay, let me write down the hint. So 0, 1, -1, and so on, maybe 2. Yeah. Always try with something that's computable first. See if you can see anything. This example is very important for future. In future, we'll keep looking at this type over and over again. This type of sequence. Trying. You already done? Already done. Okay. What do you get? Bigger than -1, smaller than 1. Okay. So let's write down. So, so let me just draw it first. So you're saying that bigger than -1 up to 1. So just the sequence for in the real. Okay, right. Okay, so let's show this. Okay, let's show this. Why is this true here? One is not included. Or you think that one is not included? Yeah, it's included. Okay, it's actually included. Okay, let us discuss. So let's see. So there are few things to do here, right? There are few things to do here. So if you want to say that it converges here, that means you need to show that everything less than -1 diverges. Anything more than 1 diverges. Okay, converges at 1 and between these things. Okay, I mean just between -1 and 1, and on 1 also converge. Okay, so you need to show all these. So one by one. So we break it into one by one. So let's write down the algebraic form. So our claim here is, my claim is, it is 0 for 0 up to 1, infinity for r equal to 1. And then any point I haven't covered. So I cover everything after 1, between 0 and 1. And then smaller, I didn't cover, right? Let me see. Okay, so their category is like not infinity. So let me see how to say. Okay, so okay, let me write down first. So I cover 0 first. Okay, let me let me put here equal 0. Okay, and then I add more stuff. Add more stuff. 1 when r equals to 1, and then maybe I don't put infinity. I just put diverges for r less than minus 1. Okay, because later we'll see why. Okay, this is my claim. Okay, so in this case, I will cover everything in the real line. First, check that I already covered everything in the real line, and then we check that whether these cases are true or not. Okay, so this is my claim. So we need to prove this claim here. Is it? Everyone agree? Agree with the claim? I already covered everything. Have I covered? Oh, 0 to minus 1. Correct. 0 to minus 1, how? 0 to minus 1. Okay, actually also 0. So let us just increase this range. Up to minus 1. Okay. But not including minus 1. Okay. Agree? We already include everything in the real. Okay. So now we need to check these 4 things. Okay. So maybe what? Maybe we check some proof. Okay. So can we prove for 0 up to 1 first? Okay. So limit n to infinity Rn is 0. Does anyone agree or not? Does anyone agree with this? If you don't agree, I should write it in another form, maybe more easier to read form. So maybe I can take 1 over n, 1 over m of n for some m in n. Right. So everything between, so this one is for so everything between 0 and 1, not 0, we can write it as some fraction. Okay, not 1 over m, maybe m over n. M over n such that m is less than n. Okay. And this converges to 0. Is it what you learn in calculus 101? If you keep taking power for number less than 1, between 0 and 1. Assume this one is learned in previous course. This should be 0. Right. If you imagine you're taking 0.1, you square it, you get 0.01. You square cube it, 0.001, 0.0001, and then keep going on, and then you will approach 0. Okay. Okay. But for 0 point, for the point 0, it's obvious, right? You get 0. Okay. So this is a constant function, constant sequence. Okay. So we settle point between 0 and 1. So we need to settle for -1 up to 0. Okay. So for this point, you also get limit equals 0. So why is it true? Okay. So one thing you can do is you can see that okay, let's just write out what happened first. Then later we'll see how to fix it, how to deal with it. So we are considering r to the n, okay? But this number, this r is negative, right? So that means if you take even number, even power, you will become positive number. You take odd power, you become negative number. So you kind of oscillate between positive, negative, positive, negative, positive, negative. Okay, right? But you also know that if this number, absolute number of this number, lies between 0 and 1, because if you take absolute number, it lies back into 0 and 1, right? The limit is 0. Right. Okay. So how are you gonna fix this? Any idea? So you have an alternate number that you guess that will converge to 0. So how you deduce for the original sequence to converge to 0? Does everyone get the question first? Everyone must get the question first. If you don't get the question, then there's no point for you to figure out the answer. So you need to understand what's the question first, and then together we will work out the solution. Anyone not getting the question? Does anyone get the question? Does anyone get the question? What you want to solve? Okay, so you got an alternating sequence that if you take absolute value, it converges to 0. How you show that this alternating sequence converges to 0? Okay. How? Use the example. Yeah, use the example we proved earlier. So what is the example we just did? Okay. Why I can't find it now? Yeah, here. So we show that if the absolute value of that sequence is 0, then actually the original sequence also converges to 0. Okay, so we're trying to use this example here, or we call it proposition for now. Okay, call this a proposition. Okay, so how to use this? So to use this, okay, you need to establish that. Okay, let me write down. Okay, let's call that a proposition. So let's label this as a proposition. Since we don't have proposition for now, so we call this a proposition. So proposition is something that's not as big as a theorem. We will call it a proposition. So maybe we call it proposition. So if by proposition, by proposition. Okay, now I'm teaching you or guiding you how to use a theorem. Okay, if by the proposition, if okay, what we want this thing to be 0. Okay, this is our claim. Okay, so by proposition, if lim n infinity of the absolute value of Rn is equal to 0, then we will get what we want. Right? Is that right? So now we reduce our question to P. So I mean, if P then Q. So we reduce our question to this. Is this true? Is this true? Why? Why is this true? Why is this true? Why is it? Which proof? Which proof? Oh, yeah, right. Correct. Yeah, you are right. So if you take the absolute value, then the whole thing will lie back to 0 and 1. Then we already proved that in between 0 and 1, this sequence converges. So what? So by proposition, we get that the alternating one also converges. Okay, let me write down. Not that we have limit n infinity Rn is equal to 0 because this one lies, this one lie between 0 and 1. Let me see how to put it. lie between meridian, and hence absolute value of Rn is equal to and not hence but n, the absolute value of R. So the R to the power n and taking absolute is the same as you take absolute first and then you multiply by it. Okay? Is that okay? So you reduce the question to something between 0 and 1. Okay. So the key part is this part here. This part. Okay. So if you does everyone see this or not? Does everyone see this? So if you get a negative number after modulus, you get positive. It's the same as you make it positive first and then you take whatever power you want. I think this one is a simple arithmetic. Okay? Because yeah. Okay. All right. So we have shown this, and then what else we need to show? Okay. So let's see for. So we have done what? Let us write down. So we have done this part here. Okay. Let's show the second part. So R greater than 1. So for R greater than 1, limit of n to infinity, Rn, is it clearly infinity? Is it clear? Oh, clear. Okay. Okay. So everyone agree with this? Okay, so we can skip this. Okay. Okay. So how about R equals to 1? Okay, so R equals to 1, you are just taking the constant sequence. So it's just 1. Okay. What else? When R is less than equals to -1. Okay, so when R is less than equal to -1, what happened? Okay, so what happened to this? What happened? Say again. Oh, does not exist. This one does not exist. Why? Do you know why it does not exist? So, okay, I see some of you have some gesture. So for Rn, it increased infinity, right? So, but this one is also like something like this. Okay. So it's kind of like the -1 and 1 case, but you scale every -1 and 1 with a bigger number and bigger number, bigger number, bigger number. Okay. So the limit doesn't exist. Okay. Anyone confused? Not confused? No, I mean, it's natural to confuse, but you can ask. Yeah. Any question or no? No, I mean, if some of you see it, then it's easy. But if you just can't see it, then it will be hard. So I can explain if you can't see it. Okay. So maybe I explain a little bit. Okay, I explain a little bit. So, just pick one number, one favorite number you like. Okay. So, I mean, I equals to -1. What is this? I think this one we look at it before, right? -1 to the n. Okay, just 1 n, 1 minus n, 1 minus n, 1 minus n. This one I look at it before. We already deduced that this one doesn't have a limit because if you pick any limit point, then there will be another point that's further away. So, how about -2? Okay. So what happened with -2? You will get -2, 4, and then what else? -8, 16. Okay, so you get -2. Sorry, Okay. Sorry. I think this picture a bit misleading. Okay, maybe we put like this. Okay, this one good. So I put -2, 4, -8, 16, and then what's the next? 32, and then 64 like this. Okay, so it's alternating but increasingly. Does it make more sense now? Make more sense now? Hello. No response. Does it make more sense now? Okay, so the limit doesn't exist because diverge in two directions. Okay. What's next? Yeah, we still have time. Keep going. Let me see. So if you see some of the example in the text, I will leave it as exercise as well. Let me see if we want to do. Okay, there's one thing is worth mentioning. So the next, if you see the previous notes, I will leave the next one as homework. Let's go to this theorem here. Theorem. Okay, this theorem is actually how I started to learn the continuity. I'm not sure it's the same as yours or not. This is the sequential definition for continuity of a real value function. Okay, so what does this mean? So if you have a sequence that converge to L, okay, and this sequence, right, lie inside your domain of your F, okay, so it converges to L. So the picture in your mind should be something like this. So you got A1, A2, A3, and then converge to something in L, okay, something to in L or L here. So you have a dot, okay, convert to L. And then you have a function that is like continuous here, okay. Then the result is you can take your F and then you evaluate your F on this point, okay. You can evaluate, you can see that it's quite random somewhere before, finite term before, but as close to this L here, it is really evaluating your F at L, okay? Or in other words, F of lim and an. Okay. So if you have a sequence on the domain and then you apply function to it, you also get another sequence, right? Right. Is it true? Okay. So you get another sequence. So what does that sequence converge to? Actually, is F applied to the original, the limit of the convergent sequence. Okay, let's look at an example. So example, find the lim and infinity of sine pi over n. Okay, for example, you want to find this. Okay, so you can try some number. So what is sine pi? 0. Sine pi is 0, right? Okay, so when we talk about this pi, right, this sine, right, so you should have a sine graph in your mind. So there's a pi, 2 pi, 0, right? All right. So sine pi is 0. Sine pi over 2 is 1. Sine pi over 3 is what? 60. 60 is what? Sine so opposite. Okay, I think something like this. Okay, and then so on. Okay, try to find the limit of this guy. Okay, seems like a bit hard. So you can use the theorem we have. So sine is a continuous function. All right. So sine is continuous everywhere, right? Everywhere is continuous. And inside here we have a sequence. correct? Power pi, power 2, power 3, power 4, power 5, power 6, power 7, power 8. So what does this sequence converge to? 0. Okay. So since pi over n converge to 0 for n greater than infinity. Okay, so this is a shorthand notation for limit. So pi over n converge to 0 when n go to infinity. Then limit n and a sign is continuous at 0, right? This is the condition you need to have, right? So you need to have the limit of the sequence in the domain, you found it, and also the function is continuous at that limit, then you can use this. Okay, so you can use this since this by theorem above lim n infinity sine power n is equal to sine of taking lim inside power n, which is sine of 0, which is 0. Okay, so you can see from here that lim actually run inside the function. Okay, so the limit commute with the function. Okay, if the function continuous at that, the limit of the domain. Okay, this theorem here says that the lim operator commute with your function. Okay, when it commutes when f is continuous at that limit. Okay, only it commutes. If it doesn't continuous, then you don't simply commute it. Okay, maybe it doesn't achieve it. Maybe it run to the other place for this part. Okay, so make sure it's continuous. Okay, so before we end, we still have few definition to go. So okay, so we have classified few sequence here. So we say that a sequence is increasing, okay, increasing or strictly increasing. Then for every an plus 1 is greater than an. So when you go to the next term, it's strictly greater. And non-decreasing if it is not strictly greater or equal to. Okay, they can be equal. So it can be something like, okay, so I should draw some picture for you to see. So increasing will be something like this. Non-decreasing will be like this, maybe stagnant for a while, increase, stagnant for a while. Okay, it's not increasing, not decreasing, but also not increasing. Okay, never mind, a bit weird saying that. Okay, decreasing is going downward. Okay, non-increasing is like going down, maybe stagnant a bit and then going down, something like that. Okay. Okay, so a sequence that is just increasing or decreasing is called strictly monotonic. Okay, so in monotone, meaning keep going on. Okay, just mono is one, right? Mono. Okay, so strictly monotone. And then non-decreasing and non-increasing is monotonic sequence. So it's still monotone, but it's not strict. Okay. So all these are monotone anyway. Okay. If it is strictly monotone, then that means it's increasing or decreasing. So far, okay. I think there's nothing special here. But just take note of these greater, less than, or less than and equal to, or equal to. Okay. Okay. Another definition is this bounded sequence. So a sequence is bounded above if there is a number m such that an is less than m for every n greater than or equal to 1. Okay, so that means you can find an m that bound everything, that bound all the sequence. Okay, so okay, let me introduce another notion first, then we will talk about examples. A sequence an is bounded below if there's a number m such that an is greater or equal to m, little m, for all n greater or equal to 1. Okay. If a sequence is bounded above and below, we will say that it is a bounded sequence. So it must be bounded. Okay, let me draw it. So it must be bounded above and below. Okay, to be bounded. Okay. So bounded below is something like the EX. So it's bounded below. Okay, bounded below here. Okay. And then bounded above, maybe you can think of a long X. Long X not bounded above, right? So what is bounded above? I think if there's something obvious one. Okay, I don't know, but let me draw something. So you want something to bounded above, so you need all your sequence that's below some limit, some M. Okay, I put this as M, this one in M, and then maybe I draw some graph like this. Okay, just a piecewise of 1 over X, maybe minus 1 over X. Okay, okay, okay. Let me see. Okay, maybe we stop at a theorem and then we will go. There's actually example on this increasing and decreasing. Do you want me to do it in the next lecture or you want to do as homework? Then we won't revisit. You want me to do as example in next lecture or you want to skip? I mean, for example, to show something is increasing, decreasing. You want to do as homework or you want me to show in the class? Do in the class. Okay, I will do one in the class. But today I will stop at one theorem here. I want to stop at one idea and then we can go home. So I want to start at this theorem here. So it's a monotonic sequence theorem. So I want you to think at home about this. So monotonic sequence theorem says that every bounded monotonic or monotonic sequence is convergent. Okay, so this one give a condition for what? Oh no, I mean this characterize all the bounded and monotonic sequence. Okay, so if you found that your sequence is bounded and monotonic, these two conditions together, you will know that your sequence is actually convergent. Okay, maybe it go very wild. Okay, I mean wild meaning the number, you can't see the pattern. But if you can show that this sequence is bounded, first, second is monotonic, either decreasing or increasing, then it is convergent. Okay, you should think of it. If it is keep increasing or if it is keep decreasing, but you got a bound, so it must somehow reach that bound, right? If you have a bound, but you keep increasing only, or you keep decreasing only, so you will definitely reach the bound. This is the idea. Okay, so it will converge. I'm not sure we will prove this or not, maybe not. So, okay, so one last thing to remember is this. Then when is it? The next class? First Wednesday, Friday. Okay, so Friday we will revisit the example for increasing, decreasing, and then some example for monotonic sequence theorem. Okay. Okay, see you on Friday.
Like in assignment or in task,
Yeah.
of this like limit x process infinity for one over